Right. Hello, seventh grade on level class. I hope everyone is doing well today. I know that sometimes these slides might appear small, so I'm going to read them all. I'm going to try to be very clear. I tried zooming in, and it will not let me zoom in while I'm recording this in Google Slides, and I don't have PowerPoint. So it's a little frustrating, but hopefully for the most part, you'll be able to read it and see it. And if not, hopefully I can help you through that. Sorry again about the noise. I do have a printing, and kids are around, so distance learning. All right, let's get started here with what we're going to learn today. What are we going to learn today? Oh, thanks, computer. To find the probability of independent events and the probability of, you guessed it, dependent events. So first thing we got to know is, what is that? Well, we've talked about it before, but just to give you real plain, clear cut, because I don't know that the book defines it. Independent events don't affect one another. So, flipping a coin and pulling a marble out of a bag. If I flip heads on a coin, then that is not going to affect what marble I pull out at all. If I flip a tails, same thing. No effect on which marble I could possibly pull out. Now, dependent events do affect each other. So if I'm pulling a card out of a deck, or let's use the marbles. If I'm pulling marbles out of a bag, I pull a red one out. Well, that does affect my next event, because now there's one less red one. So it could be different now. I might have gotten that one. Who knows? Now, if you put the red marble I drew back in the bag, then would that be an independent or a dependent event? It'd be independent. It would have no bearing on what the next one is. Just like it's like rolling a dice, rolling a number cube, and then rolling it again. You're doing the same event twice, but it doesn't affect the outcome from the first to the second. So that's the difference between independent and dependent events. So, the probability of two independent events can be found by multiplying the probability of the first by the probability of the second. We already have been doing that, right? So we said rolling two die. You roll one, roll another, there's 36 possible outcomes, because 6 times 6 is 36. So the probability is 1/6 times 1/6. We've done that. So let's look at another example of what we've been doing. One letter tile is selected and the spinner is spun. What's the probability that both are a vowel? Well, the first way you can do it is spend a bunch of time and a bunch of ink and a bunch of paper and make a tree diagram and say, oh, if I get a G, then I can get GABC. If I get a B, I can get BABC. If I get an E, I get EABC. If I get an A, I can get ABC. So your sample space, this is your possible outcomes. 3, 6, 9, 12. Wonder how we could have gotten that a little easier. How about multiply? Use multiplication. Like my laser pointer. And the probability of spinning a vowel is what? 1 out of 3, because there's only one. So I zoom past this on the first method, okay? But you would have also seen that, one vowel, one vowel, one vowel, one vowel, one vowel, blah, blah, blah. All right, the probability of getting one here is 1, 2 out of 4, which is 1/2. So you do 1/2 times 1/3 is 1/6. Same thing here, okay? But the only difference is here you had to find which one has vowels. 1, 2, 3, 4, 5, 6, 7, 8. All right, which one of those 8 are both vowels? Let me see. 1, 2. So 2/12. Just more work, more time consuming. Don't recommend it. Welcome to do it though. Anywho, let's try one, shall we? 2 spinners are spun below. What is the probability that both spinners will show a number greater than 6? Pause now and work it out, but be careful, don't rush. Think. Pause. Oh, you're back. Use not yellow. Use pink. So the probability that both spinners will show a number greater than 6. Well, what's the we could make a chart, right? We could make a chart and it would be a lot because there are 10 possible outcomes on the first one and 10. We have to make 100. 100. I'm not doing that. I'm going to use multiplication. So how many possible outcomes are there in the first wheel? There are 10. How many favorable? Favorable meaning numbers greater than 6. Well, there's 7, 8, and 9. So there are 3 favorable outcomes in the first one. And since the second wheel is exactly the same, and it also has a 3 out of 10. And it's an independent event because it doesn't matter what you get on this one. It's not going to affect your possibilities on this one. So we multiply these, we get 9 out of 100. So 9 out of 100 or 9% chance that both numbers are greater than 6. Let's make sure that we're correct on that. And we are. Go us. Go us. Okay. So it says the spinner and the number cube shown are used in a game. What's the probability of a player not spinning blue and then rolling a 3 or 4? Well, first, let's tackle the first option. These are independent events because the spinner does not affect the outcome of the cube. So first, find the probability of each event, starting with the first one, because if you don't get that, then who cares? So not spinning a blue. What's the probability of not blue? Well, there's 1, 2, 3, 4, 5 possible outcomes, and 4 of them are not blue. So 4/5. Pretty good odds. And then rolling a 3 or 4. Well, how many possible outcomes are there on a dice? There are 6. And how many are 3 or 4? 2, which is like 1/3. So let's multiply 4/5 times 1/3, and we get 4/15. So the probability of not getting blue and then getting a 3 or 4 is 4/15. About 30% odds. It's not horrible. And if you want to check, it says make a tree diagram. Why? Why would you need to check that? It's simple math. You multiply the probabilities. Don't waste your time. You know me. I'm always telling you to check, check, check. Be careful. Be careful. That is silly. Silly. Waste of time. Don't do it. Unless you just like making trees or lists. And who am I to judge? Who am I to judge? A red number cube and a white number cube are rolled. The faces of both cubes are numbered from 1 to 6. Well, since they're a cube, I would think, there's 6 sides. What is the probability of not rolling a 3 on the red and rolling 3 or less on the white? So we've got to find the two probabilities and multiply them together. Probability of not rolling a 3. Well, on both dice, there are 6 possible outcomes. Correct? Of course I am. Of course I am. And how many favorable outcomes? Not rolling a 3. Well, there's 1, 2, 4, 5, 6. Who would have thought? All but 1. And then 3 or less. So 3, 2, 1. There are 3. So we could obviously make this 1/2. And we could multiply that and get 5/12. Now, if you really wanted to make a list of all the 36 outcomes, be my guest. We've done it before. Why do it again? No, thank you. Okay? Moving on. Dependent events. If two events A and B are dependent, the probability of both occurring is the product of A and the probability of B after A occurs. In other words, probability of A and B equals the probability of A times the probability of B following A. I know, it makes it sound so confusing, doesn't it? It's still multiplying the probabilities of both events. You just have to be smart. Think about how one affects the other. So in example 3, it says there are 4 oranges, 7 bananas, and 5 apples in a fruit basket. Ignacio, I like that name. Ignacio. 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 I'm sorry. I'll shut up. Selects a piece of fruit at random, and then Terrence. Wow. You go from Ignacio to Terrence. Selects a piece of fruit at random. Find the probability that 2 apples are chosen. So we're going to find the probability of both events. It says Ignacio selects one and then Terrence. So Ignacio gets to go first because he has a sweet name. So let's look. They are dependent events. The probability of the first one, there are 4 plus 5 plus 7, 16 total pieces of fruit. There are 5 apples. So the odds of Ignacio choosing a fruit that's an apple is 5 out of 16. If he gets one, well, then there are now only 4 apples, and there are now only 15 pieces of fruit. Right? Of course. Of course I'm right. I'm going to talk real hard like this. So when you multiply those together, you could use a little cross canceling here. I highly suggest it. You can see that, you can see that 5 and 15 share 5 as a common factor. You see that 16 and 4 share 4 as a common factor. You can go right to 112. So the probability that both people choose apples is 1 out of 12. Need another example? Yeah, you do. I know you. You need one. There are 4 red, 8 yellow, 6 blue socks mixed up in a drawer. Sounds like my drawer of socks. It is so hard to find. Actually, my drawer is empty. There's a big basket full of my clean clothes right now. And I keep on digging through for socks that match. Infuriating. I spend so much more time digging through my clean clothes trying to find my socks than if I would just put my clothes away. But I'm not smart. Once a sock is selected, it is not replaced, making it a, say it with me now, dependent event. High five. Find the probability of reaching into the drawer without looking and choosing 2 blue socks. So the first draw. There are 12 plus 6 is 18. There are 18 socks in that drawer. And the favorable outcome is a blue sock, so that'd be 6 out of 18. Or 1/3. If we get lucky and we get a blue, then what is our odds of getting another blue? Well, there are now only 17 socks because we took one out, and one of them was blue, so there's now only 5 blue. So it's 1/3 times 5/17. There's no cross canceling we can do, so we just multiply across and we get 5 over 51. So the odds of you getting both socks when you're sleepy in the morning, when you have this combination, is not great. You're going to end up going again and again, and you're going to get frustrated, and your mom's going to be like, "Where are you? Your Eggos are getting cold, and we're going to be late for school." It's not good. Not good at all. How did what you learned today help you answer the question, how can you predict the outcome of future events? We've answered that question several times. So, I hope you did learn something today. I'm going to go full screen all on y'all. Watch this. How did you do today? Did you understand the difference between an independent and a dependent event? You didn't? Oh, well, go back and watch this again. I mean, I'm sure it was super entertaining, right? I had a great time making it. You should have had a great time watching it. If you understood those, did you understand how a dependent event affects the other event? Did you understand how to change your probability so that you could multiply them together? Did you learn that drawing out a tree is ridiculous? Good. Well, then give me a fist bump. Yeah. Look at that. Hairy knuckles. All right. Have a great day, y'all. See you tomorrow.